Hello and welcome to another video. In this video, we're going to be working on maximize the number of target nodes after connecting trees to. And so this one's going to be very similar to yesterday's, so I definitely recommend doing yesterday's. But in this one, you also have two graphs, and you have edges to connect the graphs, and they basically tell you it's trees. So what does that mean? There's no cycles, and there's only one path from one node to any other node. Those are definition of trees. And also for n nodes, there's n minus 1 edges, definition of a tree. And so now, instead of having this k, they tell you that a node is target to another node if the path from U to V is even. And the node is always target to itself. And so they tell you for every node, you can make any edge you want, and then you want to maximize the number of nodes target to that node from both trees. So yeah, so let's go over through these examples. So in the first node, they tell you can do this. And then for this node, it would be this, 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 and this would all be even to it. So 3, 4, 5, 6, 7, 8. And then for node 1, you can connect it to node 1, which would be here. And then that would be that, and then this, I think. 6, am I missing one? Probably. Let's see. Node 1. Oh, actually, sorry. It was node 1 is connected to node 4. Node 4 is over here. So it'd be this, and then, yeah, this, and this. So there's 5 here and 2 here, so 7, and so on. So they tell you, like, this is how the connections are made, and that's how many you get. And then in the second example, they tell you for every node, connect that node to any node of this other one. So there's going to be like a couple things you need to notice, and we can just do all that from this first example. So number 1, the connection you make doesn't matter for the first tree's count. Like this node, for example, has 1, 2 even neighbors and itself, no matter what I make here, right? If I make this or whatever, like this is the same. And so how can we, for a tree, and also the constraints are like 10 to the 5th, so we need a linear solution here. So how can we, in linear time, figure out, like, for every node, how many nodes are even to it? And so I kind of figured this out just by looking at the problem and just trying different things. But basically what you can do is you can do a BFS from any node. I thought you'd have to do from Leap, but you can actually do it from any node. So let's say we pick this node. And then we can basically mark the distance of every node to that node. So this will be 0, this will be 1, 1, 1, and 2. And then every odd number will be even to itself. And it's obvious why if they're on two sides, right? If I have like a 3 here and a 3 here, and I have to go through this node, then this is even. But even if I don't have to go through this node, like let's say if I have another example where like this is my node I'm comparing to, and this is 2 and this is 2, they are also even to each other. And if there was some more stuff, like let's say this was 3 and this was 3, these would also be even to each other, right? 1, 2, 3, 4. So basically, we can write this down. So for a tree, we can BFS from any node and do like a level order traversal where we record distances, or just BFS and record distances to that node. Then we can group odds and evens into the same group. And so for every node, we would basically mark it odd or even and then have a counter. So like let's say we go from here. So this would be even because it's itself. This would be odd, 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 even. And so there's 2 evens and 3 odds. And each one of these nodes, like 0, for example, has 2 more in its group. That means there's 3 total nodes here. Same thing here. And you can do the same thing on this side. So let's say this is our starting node. So this would be even, odd, even, even, odd, even, even, odd. Okay. So now we have like the first part, right? Like for a tree, no matter what node, all we have to do is just figure out what group is it in, and is it even or odd, and what's the count. So like this would be 2, this would be 2, this would be 3, and so on. But then what's the optimal connection? So it turns out, because they tell you that there's 2 or more nodes in the tree, you can always make a connection where your node will be even to one of these groups. And I can show that here. So like, let's say we want to make this node even to all the even groups. We would just connect it to an odd node. So if we connect here, now this is even to all the even groups, right? Like 1, 2, 3, 4, 5, 6, and so on. And if we want it even to all the odd groups, we would connect it to an even. And by definition, if a tree has at least 2 nodes, there has to be at least like 1 odd and 1 even. So basically, to calculate this guy, so we do this BFS, and then the answer is group size for our current node plus the bigger group size for the other tree. And so now we can quickly, easily figure this out. So here, like, we have 2 odds and, or we have 3 odds and 2 evens. And here we have 1, 2, 3, 4, 5 evens and 3 odds. So we can really easily, quickly get our answer now. So basically, like for this node, this is in this group. So we're always going to want to connect with the even group. So it's whatever group we're in plus the bigger group here, because the even has more nodes. So this is 8. This is also 8. This is also 8. And then this is 7, 7. And so if we go back and look at the actual thing here, so it's 8, 7, 7, 8, 8. And that's basically it. So essentially you have to figure out that you have to BFS from any starting node and calculate this like distance. And then everything with the same, mod 2 distance is going to be in the same group. And then you can also realize I can always connect one group to the other group depending on where I make this connection. Because if I want an odd to connect with an even, then I just connect it to an odd, and then every even will be even distance. If I want to connect it with the odds, then I connect it to an even, and then every odd will be an even distance, and so on. But that's basically our answer. So let's take a look at the code. And I do think it's pretty hard to come up with these things. Like, once you see it, it's not that bad, but it's hard to come up with them. So you just calculate n and m based on definition of a tree, because a tree has edges plus 1 nodes. Then I just had a helper function to build a tree, kind of like yesterday. Then I had a function that ran the BFS for both trees. So essentially you just have a depth, and then you just run it from your current node. So you have a depth, and the depth is just like a number. And then you turn that depth into a group. So if the depth is odd, you put into one group. If it's even, you put into another one. So count parity, that's all that does, is basically if the depth is odd, it'll put into one group. If it's even, it'll put it into another group. And then finally we get our answer. So we loop through all of our nodes and we check. If we're even, then what do we do? And if we're odd, what do we do? So if we're even, then we take the even group from our tree plus the biggest group from the other tree. And then if we're odd, we take the odd group from our tree plus the biggest group from the other tree. And that is basically it. And so, yeah. So this is, I think I wrote it. Yeah. So it's n plus m time, because we're doing a BFS only on one node for each trees. And it's also n plus m space, because we're storing like the parity and depth and all that stuff. Yeah, so I want to say like the coding is easier for this one than the one before, but coming up with this stuff is maybe not super intuitive. But what I would recommend for these kind of problems, like my first suggestion was like, what if I just start BFSing at a leaf node? Like, can I get some pattern? Because I know for sure that I need to figure out a way to traverse this tree in linear time and get all the group and get the even count for every single node. Which means you can either do like a BFS a couple times or a BFS, DFS or whatever. And I was just like, okay, what if I do a BFS from a leaf node that has no other things? And I noticed like this would be even, then it would be odd, then it would be even, and that worked. And then I was like, okay, what if I try another node that's not on the edge and it works for any node? And same thing here. And then also, yeah, you do have to recognize that like, because my trees are length 2, I can always connect one group from here to another group from here, just by connecting it to the opposite one, essentially. So yeah, that's going to be all for this one. So thanks for watching, and I'll see you in the next one.